Hello again, engineering students. This is Mr. O and second question of uniform distributed loads. Same as the previous question, we're going to try and work out the reactions and the supports for this, I'm going to say simply supported beam, but it really is an overhanging beam as well. First things first, we have a look at this and we redraw it. We draw it so that we get clarity as to what we have. We have a beam and it is overhanging with a 14 kilonewton load at the end. It also has, from the far left hand side right the way across this beam up to, from the fixed and or pinned support all the way through to the roller support, it has a UDL, so uniform distributed load. So let us try and solve this. It also says that it is 6 kilonewtons per meter. So the load is uniform. It's across that point there, but the beam carries on to the side over here. And we've got some distances. We've got some distances which is 7 meters to there and to the end 3 meters. So the whole beam is actually 10 meters long. And of course, this is going to have a single load. This is the reaction at the right. This is the reaction at the left. And from we know, we're going to have a force applied to that beam that way and a force applied to the beam that way. We don't know what it is, so we're going to assume it's positive. And in our vertical and horizontal equilibrium forces, we always make up positive and right positive. This will have a force supporting that beam as well, we assume to be positive. This one is going to be called force left horizontal, force left vertical, and this one's going to be force right vertical. Okay. Straight away, I need to solve what is the total load across this beam that's applied by this uniform distributed load. I'm going to do it on the side here quickly. So UDL 1, because there is only one, I'm going to try and get the total load of it. So let's work this out. It is 6 kilonewtons per meter. How long is it? 7 meters. You can see by the drawing there, it is 7 meters long. Times 7 meters. The 2 meters cancel out, gives us our force. 6 times 7 is 42. Let me do, this is going to be so silly, me actually working this out in the calculator. 42, yeah, you never know. You go a bit crazy when you're doing exams or you're under pressure. So this is going to be 42, a total of 42 kilonewtons downwards. That's what the force that this question, this UDL is applying to this load, this beam from there to there. Let's find its center point though. Where is the concentrated load that is supposed to be? Where is the normal force that it's applying? So let's work that out. What is half of 7? Half of 7 is 3.5. So it's going to be 3.5 meters from there, from the left-hand side. That's where we simplify that load. So effectively, I'm going to redraw this here. I'm going to redraw the beam quickly. We have that, a beam, and we have that. This 7 meters, 3.5 meters, and this from the left hand side, because we'll probably take a moment around that side, is 10 meters. And we have that force to solve, this force to solve, and that force to solve, and we know what that is. 42 kilonewtons down, 6 times 7 is 42, it's 7 meters, times 6 is 42, and this is given to us as 14. And that is it. Now we really just solve a simple beam equation to solve the reactions at both of those. Force RV, force LV, and force LH. Quickly do my assumptions. I assume that the beam is in equilibrium. Because of what I've done before, all my clockwise moments around the particular point that I choose are going to be positive, and all my counterclockwise or anti-clockwise are going to be negative. And for my vertical, all my forces going up will be positive, all my forces pointing down will be negative, and for my horizontal, all my forces going to the right will be positive, and all my forces going to the left will be negative. Force vertical, force horizontal moments around the beam. Okay, let's do this. I'm going to take a moment around RR. Take a moment about RR to find RL, which is my force. Just made a mess there. So what happens when you rush. R left, R right. I find this one by taking a moment around there because I technically remove that from the equation and my beam becomes a pivot point. That point becomes my pivot point where I can work out. Sum of all the moments equals 0. Moments is force times distance. Force times distance of all my clockwise moments, subtract force times distance of all my counterclockwise moments. From that point, how many forces are now causing this beam to have a turning moment at that point in the clockwise motion? I have the UDL, which has been simplified to a single force, is 42 kilonewtons. I verified that's also kilonewtons, so my units are the same, my meters are all the same, and it is 3.5 meters from the left-hand side, from the point I'm taking the moment from. This is added with that load that is on the far right-hand side. So I have this first one there, and I have that one there. That's going to cause this beam to go clockwise. And that is 14 times, from there to there, it is 10. 7 plus 3 is 10. You got to keep your wits about you when you're doing this maths because you can make such a simple mistake so easily. I don't know what that force is upwards, but I do know it's 7 meters across. So it's going to be force RV times, see, I almost wrote 10 there, 7 meters. Simplify this. Let's do this. It is, open brackets, I do it twice, 42 times 3.5, close brackets, plus, open brackets, 14 times 10, close brackets. That will give me 287 in the positive, minus 7 FRV. Take it to the other side. 7 RV equals 287. Divide by 7, divide by 7, divide by 7 equals 41. It's a good thing. It's a round number. It makes me feel better. Not that they will all be, but it seems, you know, they're not going to make your life incredibly hard, the guys making the questions. So the force going upwards is 41 kilonewtons. It's supporting this beam over there. Now I'm going to find the next one. Straight away, we can see there are no axial or angled loads. Therefore, my force horizontal is 0. My force vertical, though, is not. And I can hazard a guess. I'm guessing that it's going to be 15. Literally, I've not seen the answers to this yet. Only reason I say that is if this is going to be 41 and my other down is 42, those two added together, the difference is 15. So let me work that out. Sum of my forces vertical downwards equals the sum of my forces vertical upwards. I also can say the sum of my forces vertical equals 0. So I go 0 equals plus the sum of all my forces vertical upwards minus the sum of all my forces vertical downwards. What are all the forces pointing upwards? Well, I don't know that because I'm trying to solve that. I've solved that. That is 0. I've solved that. I don't know what that is. So it's going to be force left vertical plus 41 minus 42 plus 14. That is FLV plus 41 minus, what does that have to get? That is 56. Negative 15. To the other side, 15 plus kilonewtons equals FLV. That was a good guess. But you start to see that straight away when the numbers work out. So, to make my, what I call it, my force diagram, it's really easy. Force there, force there, force in the middle, force there, force there. You can see that straight away by what I've done there. It's really, really simplifies. 14 kilonewtons downwards. I've worked this out to be, our right RV is 41 kilonewtons. This is 42 kilonewtons. Therefore, this one is going to be 15 kilonewtons, and this is 0 kilonewtons. And there's my force diagram. That plus that will make 56. That plus that will make 56. The two cancel each other out. And there's your answer. These uniform distributed loads are not hard at all when it comes to solving for the reactions around the supports. I hope that helps, guys. And I think I might do one more, a little bit more complicated UDL question for the next one. It's going to have all the little tricks that you might find in your exams. The weight of the beam itself, as well as changing units, because I haven't changed units yet. I've got the same units, so you've got to really be careful of either the distance or the force units changing. I hope that helps.